This is a summary of Chapter 1 of Digital Electronics. We first introduced to you the concept of analog and digital quantities. In the real world, analog quantities are generally measured in decimal numbers. So, in the real world, where it's analog, it's generally measured in decimal. Now you are very familiar with decimal because it's the number that you use every day. An example of a decimal number would be the number 78. Now what you normally see is 78, but actually, since we are talking about decimal, we would mathematically we could put a subscript below to indicate that this is a decimal number and differentiate it from the other types of numbers that we had seen in this chapter. So this is 78 base 10, or a decimal number 78. But in the digital world, decimal numbers have to be represented in binary. And so we need to be able to convert from binary to decimal and decimal to binary. To convert from binary to decimal or decimal to binary, we will use the positional value method. There are two types of binary numbers. One is unsigned binary, the other is signed binary. So we will use an example, 78 base 10, or a decimal number 78, to illustrate the use of the positional value method to convert the decimal number 78 base 10 to binary. So we will, in the positional value method, we will start by indicating the value, the place value of the position. The rightmost place would be the least significant bit and has therefore the least value. So in this case, because we are converting from hexadecimal to binary, then the least significant bit would have a value of 1, a place value of 1, followed by 2, 4, and you keep doubling it, 8, 16, 32, and 64. Next, we take this value 78 and we start with the most significant bit. Okay, we see if 64 can go into 78. If it can be, if it can go into 78, then we will write a 1. So we then have 78. We subtract off the 64, which gives us the balance value which we must put into the rest of the bits. So this will bring a 4 and this is a 14. Now 32 cannot go into 14, so we put a 0. Similarly 16 cannot go into 14, we put a 0. 8 can go into 14, so we put a 1. And then we bring this 8 here and subtract it again and we see a 6. A 6, 4 cannot go into a 6. No, 4 can go into a 6, sorry. So it's a 1. So what's left would be 4, and then we subtract. What's left is a 2. And 2 can go into 2, so this will be a 0. So an unsigned binary value for the decimal 78 base 10 is equals to 1, 0, 0, 1, 1, 1, 0, base 2. And that is your answer. Let's recap again for the unsigned binary. The conversion from decimal using the positional value method. We first put the place value for all the bits. So the rightmost one position is the least significant, and the leftmost the position is the most significant. So we have 1, 2, 4, 8, 16, 32, and finally 64. Then, having done that, we take the decimal number and we take this place value here and see if the place value can go into the decimal number, or it's, in other words, is it smaller than the decimal number. If it's smaller than the decimal number, then you put a 1 on top and then you subtract 64 from the 78 to give you a remainder of 14. And then you take the next significant bit and see if it can go into, is it greater than this balance for 14. If it's not, you put a 0, and this continues until you see the place value being able to is less than this number 14. Then you put a 1 and then you subtract the 8 below and you get a balance of 6 and so forth. So then you just read off the top and that would be your binary equivalent of the decimal.